Okay, let's get started. Hope you're all doing okay after the sudden change in the weather. You're not freezing. I guess those of you who made it here aren't freezing. Other people, we don't know. So, let's see. We are in the middle of talking about FIR filter design, which we'll work through today. And then we have a few more topics to cover before the end of the semester. We have a few weeks left. I hope you're all in a good place regarding your projects. It's definitely time to start to be getting work done on your projects. And I've fielded a number of you have sent me email indicating what topics you want to work on, and I've responded, I hope, to all of those. If you have sent email to me and I didn't respond, then please email me again. And if you haven't sent me email or spoken to the TA or spoken to me about the project topic, then please let me know what's going to happen, just to give me a chance to give you some feedback to make sure that you're on the right track. We have the final class of the semester. We have the project presentations. I've had, I think, 3 people sign up already. We can probably handle about 6 presentations. So if you want to make a presentation there, and it's really just for the pleasure of sharing what you're doing with the other people in the class, then please send me an email. And if I haven't sent you an email confirming that you're going to be on a presentation, but you think you already have asked me, then please send me an email as well, just so I can make sure I've got a list that's complete. Any questions? Okay, so we were talking about the idea of how to design FIR filters. We said that, we actually tried to solve the problem of what is the optimal finite length approximation to an ideal filter. And if we define optimal in the sense of minimum squared error, integral squared error in the frequency response, then we find that, the best filter we can do is just to copy the ideal impulse response, the inverse DTFT of the ideal frequency response, copy that over the range of samples that we've got, however long a filter we can have. And that will give us the least squared error approximation, but it gives us these filters with these weird little ringing artifacts by the transitions, which is because we were asking for least squared error rather than least absolute error, minimum absolute error, which is give us a different answer. And so that's probably not what we want, because we've got this kind of 10% error, which we don't actually reduce. We just reduce the range of frequencies that it occurs over, but we can't reduce its absolute size, which is typically a problem. But it raised the question of where that comes from, and it's like, if we're truncating this ideal impulse response, we're really just multiplying it by a rectangular window in the time domain. Multiplying in the time domain is the same as convolving in the frequency domain. And the rectangular window has this periodic sinc response in the frequency domain. And so when we convolve, we're convolving this ideal response, the rectangular response, with the periodic sinc response in the frequency domain to get this approximation to the ideal rectangular response, brick wall response, but with these ears. And we saw when we looked at the animation, the width of this transition region in the frequency response comes from the width of the central lobe in the Fourier transform of the window, and the size of these ringing artifacts is mainly determined by the size of this first side lobe in the Fourier transform of the window function. So it's nice that we could make sense of a phenomenon that we see. It's like, we can understand that. It makes sense in terms of what we know about the Fourier transform of a rectangular window and the result of multiplying things in the time domain. But it also points us in a direction like, maybe we can improve this. Instead of using a rectangular window, maybe we could use some other kind of window which had different main lobe properties and different side lobe properties, which would then have different transition bands and different ripples. So with this general framework of getting a realizable FIR filter by taking a desired response and multiplying it by a window function, we can think about different window functions instead of using a rectangular function here. Different window functions that have different main lobes, different side lobes, and get different results. And so I just showed you this slide very briefly, ended last time. But here are 4 different window functions we could use, which all have different properties. So starting off with the rectangular window, that's the one we used already. We didn't really think of it as a window, but essentially if we're just keeping some set of values in a range and throwing away everything else, that's the same as effectively setting those points in the impulse response to 0. So that's the rectangular window. And the Fourier transform here I've plotted just the abs of the positive frequency half. So it's this periodic sinc function, but now the negative going parts have been reflected up, so it's all positive. And the main lobe is here, and then the sinc function, right? It's sine x. It's actually sine nx on sine x, the periodic sinc function, but it means that it goes through 0 every time sine nx goes through pi, every time nx equals a multiple of pi, except at 0 where it's sine of pi times 0, sine of n times 0 divided by sine of 0, which gives us the 1. But it's got the main lobe, and then it's got these zeros, but in between it sort of falls off as roughly 1 over n. Right? They die away quite slowly. Well, one thing you could think about doing is if you took this function and then you scaled it down so it was the same size as this side lobe, then you shifted it over and then subtracted it, you could try and cancel out that side lobe, right? I mean, if for some reason you had a set of these kinds of functions and you could add and subtract them, then you could try and cancel out that first side lobe by a shifted version of this. Now, to shift it in frequency means multiplying by a sinusoid, right? Shift in frequency is just modulation. And shifting it actually so that it lined up here would be shifting it by 1/n of the frequency range, where n was the size of the length of the window, which is actually multiplying it by the cosine that finishes 1 cycle in the length of the window. I haven't proved this, but this is actually how it works. And then to the scaling to hang on, I got ahead of myself. Okay. That's how we get to this one. Let's talk about this one first. So this is now here the problem is that we've got a rectangular window. The reason we have these lots of energy in the high frequency is because we've got this discontinuity in the time domain. Whenever you've got something which has got a sharp edge, it's going to result in lots of high frequency stuff, right? And so that's what we see here, that the Fourier transform of this has all this high frequency because it's got this sharp discontinuity. So let's have something which is nice and smooth, has no discontinuity in time values. Well, we can just use a raised cosine, right? So this is just the cosine function, but I've offset it and then scaled it so its peak value is 1 and its minimum value is 0, right? So it's just a cosine. So here it's continuous in both slope and value, right? Because it has this kind of flat part at the bottom here. And so we just join it up here. Okay, so now, and that's just 0.5 plus 0.5 cosine, and then this is just the cosine functional complete 1 cycle here. Now we see that because it's so much smoother, we have much lower side lobes here, right? You can barely see these side lobes. They're there. We'll see them on the next slide on the log scale, but they're very small. But because we've sort of made it effectively narrower, right? It's the same, the number of non-zero values is the same. It's the same length of FIR filter, but a lot of these non-zero values are quite close to 0. So its effective width is smaller in time, and so its effective width in frequency is broadened out. That when we squeeze things in time, we squeeze them out in frequency. And so here, instead of, it doesn't have a 0 here where this one had a 0. Its first 0 is actually twice as far out where this second 0 occurs. So we have twice the main lobe at the, which is like means we've got a wider transition width, but we have a much, much smaller side lobe here, and so we get a lot back. Now, let's say this side lobe, which is still visible, was still too high to us. Now we can try and do this thing of saying, well, if we could take one of these things and add it around, then we could maybe move it over and try and cancel out that side lobe. And that's what happens here, where we actually, it's the same function. It's like 0, actually, I think, I'm not sure. So now I'm thinking something different. But this is the same function, but we've got this little bit of an offset, right? So we just have, basically it's 0.04 plus 0.5 plus 0.46. Like it's 0.08 plus 0.46 times this one, or 0.92 times this one. So the shape is the same as this one, but there's a little bit of a step here. And a step is actually introducing high frequency like this, but the high frequency is in the opposite sign, and it's just of the right size to cancel out this first lobe. So it actually makes this first lobe smaller. But what happens is that we get all these other higher frequency terms coming in, and so you're sort of trading the first lobe for the subsequent lobes, and we'll see that on the next slide. This idea of making things smoother to try and get less high frequency, you can take that further. And so you can have this so-called Blackman window, which has now not only a cosine of n term, but a cosine of 2n term. So it's getting a sort of a second harmonic, if you like, function to make it even smoother. And this is like basically making it not only the slope, but also the curvature is matching at these edges here. And so this thing now, it has very much less high-frequency energy, but it's even broader in the main lobe, right? So now, instead of having this first 0 here, the first 0 is actually out here where the third 0 was of the original rectangular window. So these are 4 different windows with increasingly broad main lobes. Actually, these two have the same main lobe width. But increasingly little high-frequency energy, increasingly reduced high-frequency energy. So if we look at that on a log scale, it's much clearer what's going on in the high frequency. The blue is the rectangular window, and you see it has the narrowest main lobe by a substantial margin. But these side lobes on a log scale, on a dB scale, are pretty large, and they die away. There's 1 over n, but they don't die away very fast. The Han window was the one where we just had the raised cosine, and so now it's the first lobe is twice as far out, and we see these things die away nicely with frequency, right? And the first one is much lower than even any of the rectangular window lobes, but it's still quite high. It's like minus 32 dB or something here. So the Hamming window is this thing where we basically take the sum of the rectangular and the Han in such a way that we cancel out this first lobe of the green with some of the blue. And so we have this extra 0 in here where they actually exactly cancel. And so this first lobe is greatly reduced. But now, if you look at what happens later on, we've got these rectangular lobes coming in at some height, and so for above the third lobe, we've actually got worse high-frequency performance than we did with the straight cosine window. So if you really care about the nearby frequencies, then you can use a Hamming window. But if you care just generally about trying to concentrate the energy in frequency, then a Han window is a better choice. And then finally, the Blackman window is even broader in its main lobe, but it's got the similar performance to the Han of having these low side lobes which die away with frequency. But now the largest one is, almost minus 60 dB, which is a nice rejection. And in a sense, it's like, well, which is worse? having a lot of, having any frequency that's sort of far from where you want it to be passed through, because the Blackman is sort of, up until here, it's worse than the rectangular for all frequencies. Or is it worse to actually have minima and then maxima? Because what happens with the rectangular window, if you have, if you actually look at the frequency response, it's like, oh, you've got the main lobe, you've gone down to a low value, but then suddenly it reappears and keeps reappearing, and so you get these sort of echoes of the frequency edge showing up, which are quite disturbing. And sometimes it's nicer just to have something that's fairly smooth, maybe fairly soft, has a broad transition band, but once you've gone through the transition band, you basically, you're not going to see any additional features showing up. And so just to remember, this would be the frequency response if we tried to build like a band pass filter for a single frequency, or for the low pass frequency that only passed DC, only passed zero frequency, then this would be the response, because that would be convolving this with an ideal response that was just a delta function. In general, we're convolving this with some other ideal response, which is maybe rectangular, and so we're going to blur this with some rectangular functions. This isn't exactly what the transition edge is going to look like, but these bandwidths and side lobe heights are going to determine the artifacts around the transition band, the pass band edge, the transitions. It's a little bit strange to have like a set of discrete choices for this. And so it's like, well, we've got this trade-off between main lobe width and side lobe height. Maybe we could have some parametric trade-off. And so there, that somebody came along, Jim Kaiser, I guess, came along and figured that out. And so the Kaiser window is an example of that. It's using these Bessel functions, these modified zero-order Bessel functions with this couple of parameters here, but it's basically now we can get an expression for a window function as a function of n, where we can choose the beta, the parameter, based on what kind of side lobe attenuation we want. And so depending on the value of the desired side lobe attenuation, then you just choose beta like this, and this expression will give you something that looks very much like one of those tapered windows. It looks kind of like a Hanning window, but it has a particular shape which just manages to balance the side lobes so they stay below some threshold. Although, of course, the lower the threshold is, the broader the main lobe width is. And it'll even, you can specify the order you need, obviously, to get a certain order for a certain transition width. To get a certain rejection for a certain transition width, you need a certain order, and here's an expression for that. Yeah.
So is it a good idea to maybe use one of the, say the Hanning or whatever, Hanning, and so to get rid of the other high frequency stuff, add a low pass filter to better attenuate the high.
Right. So if we've got these side lobes showing up in the high frequency, well, we can just put a low-pass filter on them to get rid of them. Now, we need to remember that we're not talking about the window function is not the filter in itself, right? The window function is something we're going to multiply the filter by. But, and then when we multiply it in the time domain, we're going to get convolve in the frequency domain. So that if we have some energy in the frequency domain, we're going to have this spreading. So we're going to get these ripples in our stop band. So we could use a low-pass filter on top of the window function to get rid of the high-frequency terms in the window function, and then we'd have a new window function which would have less high frequency. But to apply that low-pass filter to the window function would mean convolving it in the time domain. And so we'd end up with a longer window function, right? Which, okay, well, if we're going to use a longer window function, we could have used, a longer Hanning window or something like that. Or we could have used maybe we could have used a Blackman window, which would have been, since it's longer, now the main lobe width gets narrower because the main lobe width is inversely proportional to the length. And so, that's a different space. So you could view some of these windows as low-pass low-pass versions of the less good windows. But we're trying to do it all at once rather than do it in 2 steps. But there's definitely a relationship in there. They're doing the same kinds of thing. So let's, in practice, I've used windowed impulse responses quite a lot, but I almost always just use I prefer to use a hand window, simple raised cosine window, because it's not, normally this level of control is not that big a deal. It's like if you're only using a windowed impulse response, then it's kind of a quick and dirty thing anyway. So just using a simple cosine is normally enough. Because if you really want a good filter, you're going to do what we learn next, the iterative design. But let's just do an example of using this windowed filter process. So the specification is design a 25-point FIR low-pass filter with a cutoff frequency of 600 hertz, where the sampling rate is 8 kilohertz. The specification doesn't say anything about transition band or ripple depth or anything like this. So maybe it's not such a big deal. We can use essentially a heuristic design technique like the windowed ideal impulse response. And we can use a Hamming window, which has this nice property that it's quite narrow, but the side lobe width is pretty low. To do this, we're going to have to come up with the ideal impulse response corresponding to this specification. We're going to have to convert these passband edges to radians per sample. I sort of tried to sketch this last time, but basically, before we did sampling, we have a frequency response that goes from 0 up to 8 kilohertz is the sampling rate, and that corresponds to in the little omega in the sampled frequency response domain goes from 0 to 2 pi. And so this 600 hertz just maps proportionally. It's actually 0.15 pi on this scale. Here's the calculation that omega c is, the frequency we want divided by sampling rate times 2 pi, which gives us this. And you can remember this by thinking about the units. It's what we want is 600 cycles per second, which we divide by 8,000 samples per second, our sampling rate. That gives us cycles per sample, and then we multiply it by 2 pi radians per cycle to get radians per sample, which is the units of little omega, right? Little omega is how far the phasor advances each sample. Okay, so now what we really want is a 0.15 pi radians per sample ideal low-pass filter windowed by this tapered window. So we saw before that for this ideal brick wall filter, the ideal impulse response is sine omega 0 n divided by sine pi n. In this case, sine 0.15 pi n divided by pi n. And now we're talking about we've got 2 cases where we're doing transform, but from a rectangular we're doing a transform rectangular. When when the rectangular thing is in the frequency domain, we're doing the IDTFT, which means we get sinc function sine x on x. When the rectangular function was in the time domain, we're doing the forward DTFT, which has to be periodic, so we get the periodic sinc sine nx on sine x. But this is converting from the frequency domain to the time domain, so we get an infinite duration sinc function like this. We were asked for a 25-point FIR filter, so that means we need this is going to be our Hamming function. So it's going to have a middle point and then 12 points on each side to give 25 points total. And so we can calculate that. We just multiply them together and we get, here's our finite length tapered sinc function, which we can write out in one step like this, and for 25 points. So the question is, how does that look? let's go to MATLAB and see what it looks like. So if you go to this week's MATLAB script, here's the script to do it. Let me just copy that into MATLAB and we'll... what's that? Yeah, I thought I'd added something to there. Let's copy that into MATLAB and see what it looks like. Okay. So here's omega c. Here's my half-length 12 points. Here's my Hamming function. MATLAB has Hamming built in, so just like I ask it for a 25-point Hamming function, it gives me a column by default, so I just take the transpose to get a row here. Here's my sinc function, right? The ideal thing is sine omega c times n divided by pi times n, and then multiplying it, dot multiplying it, so pointwise multiplying it by the window. The only problem with this is that at m equals 0, or this n equals 0, and here I'm going to have 0 divided by 0, which MATLAB will give me nan, because I'm dividing by 0. If I actually look at these values to give me the, yeah, here we go. So here I'm getting just the middle three values, and there's this nan in here. But we know what it's meant to be. We know it's sine nx on x. So we can just set this by hand to be what we expect, which is omega c on pi, and then we have to multiply it by the window function at that point here. So we've manually set that, and then we can look at the result. And here it is. That's the thing we had plotted. You know, it sort of wants to be a sinc function, but by the time we get to the edge, the window function, the the Hamming function, has attenuated these bits quite a lot, so it gets squashed out quite a bit at the edges there. So if we look at the frequency response of that, here's the frequency response. Now, we were asked for a filter with a 0.15 pi breakpoint, and so here's the desired passband edge. But you see it's pretty broad, right? It turns out that a 25-point filter does not have a very good transition band. We've got reasonable side lobe height here at minus 50 dB or so, but we've got a very, very soft transition band. And there's really no way around that except by going to a longer filter. So if we instead we used, that was m equal 12, right, for 2 times 12 plus 1, 25 points. If we do m equal 32, say, so that'll be like a 65-point filter. We can do the same thing over again, I think. Yeah, so now it's 65 points, and now you can see a few more ripples of this underlying sinc function before it gets truncated. And now if we look at the frequency response of that, now it's much nicer. Again, we got our main side lobe height at about 50 dB down, but now the actual transition band is much tighter around 0.15 pi here, right? And that's, but you know, now we've got a 65th order filter, right? That's quite a lot of coefficients. That's quite a lot of calculations compared to, you know, when we tried to make a low-pass filter using like a 6th order elliptical, it was extremely sharp, extremely tight. So this is really showing you the difference between the IIR filters and the FIR filters. But, you know, on the plus side, this phase response, it's basically linear. I mean, it's got these wraps due to the zeros, but it's basically a linear phase thing, which, you know, is to say, when we look at the impulse response, you know, it's got this nice symmetric thing so that all frequencies are basically delayed to around here. There's no difference in the delay for different frequencies. Okay. Yeah. Yeah. It had two plots because it didn't. I don't know why. It overplotted the previous one. This is the phase response, but even this isn't. You know, these little jumps here are pi-sized jumps because whenever it goes through a 0 here, it has a flip in sign to get the magnitude response always the same, and so it does that by putting an adjustment of pi in here, which is 180 degrees on this scale in degrees, which is going down to 1,000 degrees. So it's kind of a misleading plot. Basically, the right way to understand the phase response is just a straight line like this, with a slope in this case of the delay. The length of the filter was 65, so the delay is 33 samples. So this slope is minus 33. Right.
Deliberately do something to make it a linear phase response?
Yes. Why is it linear phase response? We started out with the ideal zero phase impulse response, the IDTFT of the zero phase thing, which was the sinc function. We then windowed it and kept it symmetric, but then we had this 65-point filter, which MATLAB interprets as starting at 0. So it says, oh, okay, you want a 65-point filter, which is going to delay everything by 33 points. If we'd said, no, we meant a 65-point filter centered at 0, then it would have been a zero phase response. But because MATLAB assumes it's a causal filter, it shows us the delay. So here's an interesting thing. Because we've got this, if we assume that now, yeah.
Which would be more efficient in making like as we previously saw, just approximating an analog response and making an IR filter, or making an FIR filter using the windowing? I mean, like computation-wise and efficiency-wise, which would be better?
Yeah. Which is better, using the IR filter designs that we looked at before, or using this kind of windowed FIR response? If you care about phase response, the FIR filter is going to be much better because now we've got no group delay, right? There's no relative shift in. No, we do have group delay, but we've got no phase distortion. We've got no variation in the phase shift with frequency, variation in the delay experienced with frequency. But in terms of filter performance, the IR filter is much better. Right? For the same amount of calculation, you get a much, much sharper frequency transition.
Do we care about like power consumption, efficiency? I know it's all.
Do we care about efficiency? You know, it depends on the application, but mostly yes. You know, there are a few situations. Basically, it depends. Well, how much of the computation is being taken up in this filtering step? And if it's like a tiny, you know, if it's 1,000th of the computation, then if we do something that's 10 times more expensive, it doesn't really matter. It's not worth worrying about. But if it's anything like a significant portion of the computation, then you know, then we have to think very carefully. Okay, so with these effectively zero phase filters, right? If we have the filter where it is really centered on 0, we have a magnitude response which is pure real. Right? There's no, if the phase is 0, that means it's the complex number is always on the real axis, so it's always a real valued thing. And that means we can actually, when we plot it, you know, normally when we plot the magnitude response, we're ignoring the phase, so what we're seeing is not quite what we're getting. But here we can actually plot the complex valued frequency response, but we can plot it on just the real part because the imaginary part is always 0. And that means we can actually do this idea of thinking about doing arithmetic in the frequency domain. And so let's say we wanted to build a high-pass filter instead of a low-pass filter. Well, one way to get that would be to take 1 minus the low-pass filter. If the low-pass filter has a gain of 1 at 0 and 0 at 1, then 1 minus that will have a gain of 0 at low frequencies and 1 at high frequencies. So in the frequency domain, we could take something which was constant, 1 at all frequencies. We could add on the negative of our low-pass filter, so something that has a gain of negative 1 at low frequencies and 0 at high frequencies. And then if these were all pure real, they would simply add up, and we get this high-pass response coming out, where it was 1 in the high frequencies, but then these things cancel to give us 0 in the low frequencies. And we can do that with these zero-phase filters. We can't do it in general because mostly if these are complex numbers, then what happens when you sum them up depends on the relative phase. But if they're all zero-phase, we can do this. And so in the time domain, that would correspond to delta of n, which is just this function that has a gain of 1 for all frequencies, plus the negative of the low-pass filter impulse response. So just subtracting that out, which is this thing which now has a gain of -1 at low frequencies. That'll give us this high-pass response. And so in that case, it would be something like delta n minus the sinc function, or minus the windowed sinc function. Let me just show you that in MATLAB, because it doesn't... Normally, this doesn't work, right? Normally, we can't do this because the phase wouldn't work out the way we think, or we'd need to be very careful to make sure that what we were actually getting from that subtraction would depend on the relative phase of these things. But in this case, the relative phase is always 0, so we're good. But we have to make that impulse function, and we have to make it so that it's lined up with the same length and has the center at the same point. But I can make an impulse function like this. So first off, I'm making a set of zeros at the right length, and I'm just making the center point 1, right? So if I now stem h0, it's just this impulse response. And if I look at its frequency response, it's got a gain of 0 dB and the same linear phase response that we had before, but now it's managed to unwrap it all the way, so it's going down to -6,000 pi. So now if I have h is equal to h0 minus my low-pass response h, right? So remember, h looked like this. So hh is going to be the negative of that with a 1 in the middle. So hh looks like this, right? So it's the negative of this thing, but then I added a 1 in the middle. This windowed thing only had an amplitude of like less than 0.2, so this thing sticks out in the middle. But that's all it is. And now if I look at the frequency of this, it's this very nice high-pass filter, again with -50 dB ripples and then a nice flat gain of 1 for high frequencies. And in a way, you can sort of view this as like, well, of course it's got lots of high frequencies, it's got massive discontinuity, it's got this spike in the middle. But there's a little bit of low-frequency stuff around here, which is actually counterbalancing for the very low frequencies the energy that's passed by this spike, so that we take out the low frequency, right? The average of this thing, which is the gain the constant signal would experience, the average is 0, or close to 0 anyway. Should be exactly 0. So, right, mean of h0 is much larger, yeah. So that's what we're seeing there. Okay. Any questions about that? All right, so that's one way of building FIR filters, and it's very hands-on. Sort of makes sense, right? That we sort of used our idea of what an ideal impulse response would be, and then we just sort of built an FIR filter out of that by extracting a bit from the middle and trying to smooth it out so we didn't get discontinuities, to try and get it a little bit well-behaved. But it's very ad hoc. It's like following your nose, and it's like, in the end, what did we get? We got this filter, that actually didn't look that bad. Let's look at the original one, frequency of h. Oops. Yeah, it's. Remember that when we were trying to get our best possible filters in the continuous time domain, we like this idea that the ripples should all be the same height, because basically, if they're all the same height, then we've kind of balanced the distortion, and so we're in good shape. Here, these ripples are sort of the same height because of the way that we used in the Hamming window. We sort of tried to balance the height, but they're not exactly, right? This first one's a little bit larger. And so it's not clear what we've optimized. And in fact, we haven't really optimized anything. We've come up with a filter which is sort of doing the right kind of thing, but it's not the best filter in any sense. Right? We started off trying to minimize the squared error, and then we're trying to balance the worst case error. So we end up with this kind of compromise, which is halfway between the two. Thinking like engineers, we'd like to find the actual true best filter. And how can we do that? So here's the actual way we design FIR filters, which is by this basically iterative gradient descent technique. And the reason this is a nice problem for this kind of technique is that we've got this finite description of the filter. The filter is going to be some set of values in this finite dimensional space, the number of the length of the FIR filter, 25 points or whatever. There's going to be this 25-dimensional space, which is all possible settings of those 25 values, and then one of those is going to have the best properties according to whatever criteria we want to optimize. So we have our definition of the filter in this finite dimensional space. We have some thing we're trying to optimize. We have the ideal filter. We have some measure of goodness of fit, and that gives us an error, epsilon. One way we can optimize is to just estimate the derivatives of the error with respect to each of our coefficients, each of the h of n's, for our finite number of n's that we care about. And then we could update the h values so they move towards in the direction that reduces epsilon. We could do it by a small step, and then we could repeat. And if we take small enough steps, then we're going to arrive at some local optimum in h. If we're lucky, or if the problem has the right shape, it may be there is only one local optimum, which will be the global optimum. We'll have the best possible value. But regardless, if we start off from something that's not optimal and we do this, we can always improve it slightly to find the nearest local optimum. So this is optimization. It's a huge topic in itself, and there's lots of considerations. But here we can use it as a way of solving for a filter. And it's a very different flavor of solution than these closed form. Here's the polynomial that gives you the optimal thing you want. Here we're saying we don't have the mathematical solution, but we know how we can write an algorithm which will loop around and will find us a solution. And there's a very large body of literature on how to solve these general kinds of problems, these optimization problems. What error criteria should we use? Well, we've sort of gone through a couple. We can try and optimize the squared error, or we can try and optimize the worst case deviation. We can try and generalize this if we want. We're not really going to use this, but just so that we've seen how you could try and write this in a more general way. We could say, well, we've got our desired response, frequency response, and we've got the actual response that comes out of our FIR filter, which is now just the DTFT of the fixed length filter we've got. So it's the difference between those two. We can put a weighting function on these to say, well, maybe we care about different frequency regions to different amounts. Maybe we want to scale the size of the error in the pass band compared to the stop band. And maybe we've got regions where we don't care, where we can set W of omega to 0, so they don't contribute to the error. So we take this weighted error, and then we can raise it to some power. And the higher the power, the more large values become important, right? If we think of taking the sum of the absolute values versus the sum of the square values, then squared values tends to put more weight on larger values. And in fact, if we let the exponent go even larger, then the largest value for any value of omega comes to dominate. And so in theory, omega p equal to infinity tries to optimize the single largest value. And then we integrate that over all frequencies, or over all frequencies within a range, to give us our error function. So here, if this is our plot of the actual frequency response, and the desired frequency response has some value here in the pass band, some value in the stop band, then here's our weighting function, which is 0 in between, but has a different weight for the pass band and stop band. Here's our weighted error, W times D minus H, which is now sort of scales these differences by these different weights. And then we're raising this to the pth power and integrating it over all frequencies to get our epsilon. So, clearly there's a range of different criteria we could use for the optimization routine. If, as was implicit in the IIR responses, if we're interested only in minimizing the maximum deviation, which is the minimax criteria, then we'd use p equal infinity. But we could plug it in, we could get answers here. So that's what we're going to look for. We could let, in theory, we could let the phase response do whatever it wants to do. But we can also specify that as a constraint. So we can say, okay, we're searching within the space of linear phase FIR filters, that is filters with symmetric impulse responses, and we can write that into our optimization routine by only having now these m independent values giving us a 2m minus 1 point filter or something like that. Now, that's basically all we need to do. We can just plug it into our favorite optimizer and we get an answer out. But it's worth looking a little bit below this, below the surface here, just to see what happens. When we looked at linear phase filters before, we found that we could write this symmetry in the impulse response allowed us to write the frequency response like this as a pure phase term. This is the linear phase term. And then a pure real magnitude response term, h twiddle, where h twiddle was given by a set of basis functions. For a type 1, odd length, symmetric FIR filter, it was a set of cosine basis functions where we had, these are functions of frequency, but we could have enough ripples in the we could have as many cosine bases as the half length of the filter, as m. And so that we could have any shape we could build out of these first m cosine terms, these first m Fourier terms, if you like. So we're basically making a Fourier series approximation to this periodic spectrum. So this function, a of k cosine k omega, well, for any cosine k omega, we can write it as a function, as a polynomial in cosine omega up to the kth order. We know that cosine 2 omega is 2 cosine omega squared minus 1. And you can go up. The cosine 3 omega has a function which is a cubic, as a third order polynomial in cosine omega, etc. So that means if we have a function like this, our function with h twiddle of omega, which is for some range of k's, a of k times cosine k omega, we can also write it as a kth order or an mth order polynomial in cosine omega, right? There's going to be, for each one of these, there's going to be a set of coefficients which we multiply a of k's by. We sum them up for the same power of cosine omega and we get the alpha of k's, right? So this space of frequency responses that this particular finite length FIR filter can cover is also covered by the space of kth order polynomials in cosine omega. Now, why is that interesting? Well, because if we know that something is a kth order polynomial, we know about how many points of inflection it can have. That a fifth order polynomial can only have up to 4 points of inflection. A quadratic only has 1 point of zero derivative. A cubic can have up to 2. So you always have, for nth order, you have a maximum, at most n minus 1 maximum or minima. And so here's the relationship between them, right? We're saying that this frequency response is a function, a polynomial in cosine omega. So we plot it in cosine omega. Here's fifth order. It looks like a fifth order polynomial. But what we're actually getting is not the function we're getting the frequency response as a function of omega, not cosine omega. And so what happens is we take this polynomial and we map it through this cosine function to get a different x-axis. But for any value of omega, at least in the range 0 to pi, I can find the value of cosine omega and I can figure out which point on the curve I'm looking at here. So they're in order, right? It's a monotonic function, albeit it's flipped around and distorted. So these 4 extrema here come out to be the 4 extrema that I get in this magnitude response of this filter. They're the same values, right? but they just they come in the reverse order. And we also, in this thing, because of the way that this cosine function goes to 0, we also get local extrema at the edges here, which don't show up in this polynomial. But the reason I'm talking about this is because if I've got a fifth order polynomial here, I can only have up to 4 extrema in between, in the middle here. So this is going to turn out to be important later. And you can sort of see that falls out of the relationship to this polynomial in cosine omega. Of course, if this polynomial cosine omega had its extrema outside the range -1 to 1, then there would have been no value of omega, which gave me a value of cosine omega in this range. So there would have been fewer than that many extrema. Or you can build a fifth order polynomial that only has 1 minima as well. So you can have fewer than n-1, but you can't have more than n-1. Okay, that's cute, but it's not that important or interesting itself until we get to this. So this is where we do get kind of math coming in a kind of unexplained way. But there's a theorem called the alternation theorem, which tells us about the properties of the kind of filter that we want. It says that h twiddle of omega is the unique best weighted minimax order 2m approximation to the desired function. So this is what we want. We want the optimal minimax filter with weighting of this particular order. And we'd like it to be unique. Well, we sort of assume it's unique, that we think there's going to be just one of them. It turns out, yes, the math here has proved, the math that we haven't seen, but there is math that proves that we can find this unique filter, and we'll know it when we see it because it'll have these properties. Okay, so it'll have a set of extremal frequencies. The error magnitudes will be the same at each of those frequencies. I guess the weighted error magnitudes will be the same, which of course makes sense, right? That's what we expect from a minimax filter. The errors are the same. All the maximal errors are the same. The peak error will alternate in sign. That sort of makes sense as well, because if you've got one error which is the worst case and then another one, it has to be sort of the opposite worst case, because otherwise there would be something else in between which was not worst case. So this is all kind of obvious, but here's the surprising part, that h twiddle of omega has at least m+2 extremal frequencies. So it's saying, as long as you have these extremal frequencies which are all the same magnitude and they alternate in sign, for an order 2m approximation, we need to have at least m+2 of these extrema. And if we've got m+2 or more of these extrema, then we found the unique optimal filter of this kind. And so we know that there isn't any better one. Now, in a sense, that might be like, well, this sort of sounds like we've specified the best filter anyway. It's the one with, equal-sized errors, doing the right kind of thing. And m+2 sounds like about as many as we can have. But it turns out that it's not quite as many as we can have. So here's the picture, right? Here's a candidate magnitude response in green, the desired response in red, with the bounds, the scaled bounds in blue. And so here's the weighted error function. And here are our ripples, our local ripples, right, that came from that polynomial. And we see that apart from the ones at the ends, we've got 1, 2, 3 of them. So when we do this error function, we find that there are now, here we've circled in red each of our extremal errors. And so we get them from these ripples. We also get 2 from the band edge, right, because the optimal filter is always going to just touch that band edge here and just touch that one, because if it didn't, then we'd be able to make the transition band a little wider and still keep within bounds. And we also get points of extrema at the 2 edges, the 0 frequency and frequency pi. So if we do this kind of plot and we count up these things, if we start off with a 2m order filter, then if we count this up and we've got at least m+2 of these extrema, then we know we've got the best possible filter, that we've optimized it. That's what it means. So how many of these things can we actually get? Well, we want to get n plus 2. H twiddle of omega has at most m minus 1 extrema in away from the edges because of coming from this polynomial. So we need 3 more. But we actually have up to 4 more, because we have the 2 from the transition band edges and then the 2 from the extreme edges of the frequency range. So we can have up to m minus 1 plus 4, m plus 3 extrema like this. The alternation theorem says we need n plus 2. So we can miss one of these, but only one. If we missed one of the transition band edges, then we wouldn't get this alternation. Then if we just missed this edge, so this was not one of our red circled things, then this would be a negative one, and this one would also be negative. So we wouldn't have this property where the successive edges the successive extrema have to alternate in sign. So the only thing we can do is we can afford to not get one of the 2 outer edges. And so this is basically the bottom line, that if we have a set of plots like this, we can tell if they are the optimal filters by counting, if we know the order, and by counting the number of extrema. So here's our, this is a m equal 5, a 10th order filter. We have 1, 2, 3, 4 local ripples, right, which is the most we can have with a 5th order polynomial. And then we also have so we've got these 4 extrema in here, and then we've got the 2 band edge extrema and then 2 extreme frequencies. They're all touching the edge of our error bound, and so we have a total of 1, 2, 3, 4, 5, 6, 7, 8 extrema, which is m plus 3, more than we need, so this is definitely an optimal filter. Here's another example where we've got almost that, but this last one doesn't quite reach the edge. It goes down to some in-between value in here. But we've still got 7 extrema, so we've still got m plus 2 extrema. So this filter is also optimal. These filters can't both be optimal for the same criteria. So actually, to get this, I adjusted the weighting of these ripples slightly. So this is actually solving a different problem, which is why it is still an optimal filter, but has 1 fewer extrema. But here's a filter which misses both of these extrema, and to generate this, I had to basically fake it. Right? I had to generate something other than that was not an optimal filter. It's got these 2 band edges, it's got the 4 local things, but neither of the extreme frequencies quite hits the error limit. And so this is actually, we can look at this and we know if it's a 5th order filter, if it's a 10th order filter, m equal 5 filter, this is not optimal in the minimax criteria. There's some slight variation in the criteria where I can reduce all the errors a little bit to squeeze this one up to the error bound and get a better filter with a less total error, smaller maximum error. So that's kind of that's what the alternation theorem means, or the Parkes-McClellan FIR filter solutions mean. Again, it doesn't matter that much if we just sort of plug into our optimization and find the optimal filter, but it lets us know exactly what we can expect to come out of that. So the alternation theorem tells us that this filter exists and how many ripples it's going to have and some of the properties we can expect when we see it. We still have to actually find it. And so the way we could do that is by taking some generic optimization algorithm and trying to plug it in. But there's a very simple special case optimization algorithm that works for this particular condition. So this is just recap. We have the constraints, the desired filter, the weighting, which gives us our error function. We're working in the space of zero-phase FIR filters, which means that we just have, for an mth order for a 2mth order filter, we just have m independent values. The m independent values is a symmetric filter, which are going to have this frequency response, which is a kth order polynomial or an mth order polynomial in cosine omega. And then we've got the alternation theorem, which tells us what to expect in terms of the errors. So how do we calculate this filter? And this is the Parkes-McLellan algorithm, because it was developed by Parkes and McLellan. Tom Parkes and Jim McLellan, I think. And it's based on this more general algorithm called the Remez exchange algorithm, which is a way of finding polynomials with equal-sized ripples in them. And it's iterative, as we said we were going to be doing, but it's not actually doing the gradient descent that I described on the first slide of this section. You basically say, well, I think the extremal frequencies are going to be omega I. And then assuming that you just choose them like uniformly or something. If they were the right frequencies, then I know that my polynomial is going to have this value epsilon, the peak error at all those frequencies. And so I can find a polynomial that goes through this peak error, and also it's going to alternate in sign. So I can find the polynomial that does. I've got a bunch of points here. I can find the polynomial that goes through it. I can basically do that with Lagrange polynomials, right? Something that goes through 0 at every point except for some particular point. So then I find this polynomial, but although it's guaranteed to go through these points at these values, epsilon, it's not guaranteed that those points are the extrema. And so then it's like, oh, the actual extreme are these different frequencies. I can find out where these frequencies are and get a new set of omega i's, which are presumably somehow closer to where those frequencies should be. And then I plug them in here and I loop around. I get a new polynomial of these new set of omega i's and see if that one actually if they're actually the local optima. And then I repeat until I actually get the thing that has the local optimum. And it turns out that this thing converges very rapidly, typically in a few, 5 or 6 iterations. So this is how I was taught it. And again, it was just like, hey, it just works, don't worry about it. But it always I never really visualized it. So what I did was I tried to write a program that would actually do this. Now, it's not a full up expression, a solution to the whole Remez problem of finding the filter, but it's just trying to do that process of finding the polynomial and adjusting the frequencies. And it's kind of interesting to see how it works out. So I just want to show you that now. So we're starting off, we're trying to find a filter that basically we're trying to find a polynomial which has equal-sized ripples in this interval from -1 to 1. And we're trying to find, in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 ripples. And so we say, well, let's assume that because we've just got a single kind of range here, we can just say, well, let's assume that the ripples are between 0 and 1, and then we'll scale it later on to make it fit the actual depth that we need. But so we can find a polynomial that goes through all these points by using the Lagrange polynomial technique, by taking a polynomial that goes through just one of these points, then has 0 for all the other points, and just summing them up. And that's what we get. So here's this polynomial. It goes through each of these points, but they're not the extrema, right? They're not the local maxima. So then we find out where the actual local maxima are of this polynomial. And so these green lines are finding the actual local maxima. Because it's a 12th order polynomial, it's going to have 11 of these things. So we wanted 11, or whatever it is. I guess the edge ones don't have to be. Maybe it's 10th order, so we're going to have 11 points where it goes through this. So we take these actual extrema, and we move the points that we're trying to fit to line up with those actual extrema, right? So now I just adjust each of these red things to be those points. Now, we don't care where these frequencies in the middle occur. We just want them to be, we just care what values they are with, so we're able to move the omegas around. But we do care where the ones at the edge occur, because that's where those are kind of our band edges. So then we stretch the whole x-axis just to make it so that these things line up to be the points that we want. But now we've got a new set of constraints where we've got a set of these 11 frequencies. We know what we want the values to be there, but now the frequencies are slightly non-uniformly spaced, and we can fit the polynomial to those instead. So we do that, and we get a new polynomial. Now we've still got these very large deviations outside of our range, but things are looking a little better. In the middle, they're looking a little more well-behaved. We find the actual extrema of that polynomial again, and then we move our target frequencies to be those, and then stretch the whole thing so that our range is the same. Fit a polynomial here. Now we've got, look, all of these ripples looking pretty much the same depth. There's only these very, very edge ones which are misbehaving. Find the extrema of that. So basically these ones move in a little bit, stretch the whole thing out, and then solve again, do the whole thing over again. And pretty soon, on the 6th iteration, we've now got this polynomial which actually does have this property of being equiripple. Is it? Yeah, that's as far as it just does 7 iterations, but the 7th iteration didn't move it visibly at all. It's only asymptoting towards giving us the best solution, right? It's never finding necessarily the exact right solution. It's just a numerical approach. But, you know, for any given level of error, it quickly reaches that error in just a few iterations. And so it does that technique. And so that's basically the trick that the Ramez exchange algorithm, the Parkes-McClellan FIR algorithm is doing to find these polynomials, these polynomials that will have arbitrarily, we can have ripples in different places, you know, can have different shapes, but we'll have equal-sized ripples within each range that we care about. And you can look at the code for that if you want. It's not, you know, there's nothing magical about that. The only magical thing is, you know, using Lagrange polynomials to fit a polynomial through a set of points, but there's nothing that special about that. Now, of course, so I've just given you kind of this little illustration of an algorithm that does something like that, but even that isn't a complete implementation of the algorithm. But fortunately, MATLAB goes through the hard work of actually giving us the full algorithm and solving it. And so MATLAB has a bunch of functions which allows you to define FIR filters in a single step. And so in a sense, we could have just skipped this whole lecture pack and just gone straight to here. But now at least we know what it's going to do. So this is FIR Parkes-McClellan. You give it the filter order, which is actually the length minus 1. And then you give it the band edges as a vector between 0 and 1. So these are like these are the band edges you want. So you want a pass band between the first pair, say, and a stop band between the second pair. You actually specify whether it's a pass band or a stop band by having for each frequency a corresponding magnitude that you want. So you want a magnitude that's 1 at 0 and 1 at 0.4, so that's our pass band, and then 0 at 0.6 and 0 at 1, so that's our stop band. And then between 0.4 and 0.6 is our transition band. So they come in pairs, and then in between each pair there's a transition band. But we could have different values in here. And then for each pair, each band, we also specify some error weights. So here we're saying 1 and 2, so it's going to try and make the errors in the stop band half as deep as the errors in the pass band. But we do that, and then we get an h of n back, just like that. It's just the impulse response of the FIR filter. And here is the magnitude of h of omega. I've had to mess with this a little bit to plot it to be actual, have negative values, but it is very much this kind of shape that we looked at. And here, as you see, here's the pass band edge at 0.4, where it just hits this limit of the errors. Here's the stop band edge at 0.6. Again, it just touches that. And you can see the error is actually half as big in the stop band as in the pass band. Yeah?
So if I want to make a high-pass filter, I just flip the ones in the mainstream.
Yeah, exactly. Can I copy this? I think I can just copy this and paste it straight into MATLAB. Let's see. Almost. Okay. So 0, 0.4, 0.61, and 1, 1, 0, 0 to make a low pass here. And then what was the other thing? The error weights, 1, 2. Yeah. So let's just check that gave us what we expected. Yeah, so that's on a log scale. These things are much smaller, but if I actually took the actual values coming out of Frexy and then plot omega on pi against h, oh, it's not that hard. That's not right. Oh, because it's got the linear phase delay in there. Okay. So here's what I plotted. It hasn't rectified this part, but that's the same kind of thing. But now if I did a high-pass filter like this, where I did zeros here and ones here, then now it's the same kind of thing, but now I have the high-pass response up here. And if I actually look again at the, on a non-log scale, you can see that it is kind of the complement of that response. Yeah.
So you can specify the dB of the...
Right, exactly. Good, thank you. So we've specified the order of the filter, exactly where the bands are going to be, the gains that we're going to have, and the weights of the errors, which is the relative size of the errors. But what we haven't specified is the actual size of the errors. And basically it's going to say, it's going to find the filter that meets these criteria, that has these particular band edges and has the smallest error that just touches those band errors, it's going to find whatever filter it can find, and the one unspecified thing is how big those errors are. And so it finds the smallest error, but you don't know how small that error is going to be until you actually build it and try it out. So if you need to, if we look at the frequency response here, it turns out that our stop band rejection was only like minus 22 dB or something here, which is not very good. We need more than that. Well, what we can do is we could go for a broader transition band, so we could make it 0.35 to 0.65, right? And now this thing is, a little broader, but now we've got minus 30 dB of rejection here. Or we could up the order, of course. That's the normal thing you'd do if you wanted a better filter. So if we make it 20, and look at that, now we've got our errors at minus 50 dB, and we haven't reduced the width of the transition band, right? Because it's always just trying to match saying, well, we want the transition band from 0.35 to point whatever it was, 6.5 or 5.5, whatever. And so it keeps that the same, but it uses the extra order to push the errors down. In dB scale, right, it looks like there are no ripples here at all. That's just because these ripples, which are minus 50 dB, they're like almost 1,000th. If we zoom right in here, you have to zoom right in. Here you can see, okay, these ripples are equal depth. And of course, by design, at 0.65, it's just at the very level of that ripple, because that was the band edge that we asked for. So that's what it does. But so it conveniently finds us our filter, but the one thing it doesn't specify is the ripple depth. How does that, in the elliptical filter specification, you didn't specify the transition band, right? You specified the ripple depth and the pass band and the stop band, but then it just got as narrow a transition band as you want. Here we have a different set of criteria that we actually specify in our process. You could probably come up with, I'm sure there exist techniques where you specify the ripple depth and it gives you the filter and sets the transition band, but the natural way to do it here is to work from just the filter edges and then have the error be as large as it needs to be. So So that's it. So that's, and here's the pole zero diagram. Right, remember what we're actually getting in MATLAB is, it's just, if we stem H here, then here's it's just some impulse response. It's some set of symmetric things. It's an all-zero filter. It's a symmetric all-zero filter. So according to the things we learned about symmetric all-zero filters, symmetric FIR filters, it has to have these zeros occurring in these reciprocal conjugate constellations, right? So this is a high-pass filter. So it has a bunch of zeros on the unit circle in the stop band, giving us the ripples, the deep notches in the dB frequency response. But in the pass band, to keep it equal ripple, we have a few zeros around here which are causing the minima in the ripples, but they're pretty far from the unit circle, so they're very, very shallow ripples. But they occur in reciprocal pairs and in conjugate pairs. They occur in groups of 4 here, these ones, and then there's a group of 2 here, just to stabilize that very extreme one. But you can always, this kind of structure is characteristic of a linear phase FIR filter. Okay, any questions about that? Yeah.
So now let's say we have actually optimized the frequency response by using this algorithm to get the ripple exactly matching the pass band.
Yeah.
So now going back to the time domain, will that affect the initial, whatever window we've actually chosen to get the filter? I mean, like now the time response should be very good. So the
Yeah.
we chose initially would no more be the exact because it might also vary.
Absolutely. So this filter is different from the windowed optimal impulse response, right? It's not at all the same because the windowed optimal response had some ripples, but they were not equal depth. Now we've got some, it's going to look pretty similar, right? Because the difference may be, the difference between minus 20 dB and minus 30 dB or minus 40 dB. But what that means is slight variations of, a few percent in those values. So they'll visually look similar, but the few percent differences is a few percent down at minus 60 dB is a big deal. So it's just tuning those values a little bit to get exact cancellation in some bands.
So when we do this in MATLAB, the algorithm, so what window does that MATLAB initially choose to get the filter and then do this optimize?
It doesn't. What is it? I don't know. How does it start from? It doesn't really matter. You can start from a random place, and the descent will find it. All right. I'll see you on Wednesday, hopefully. We can talk more if you want.